Welcome to Engineering with Rosie. In today's video, we're talking carbon capture. I wanted to know how it works and whether it can possibly scale up as quickly as many projections and plans say that it's going to. So I asked chemical engineer and carbon capture expert Mark Allen to answer the big questions that I have about carbon capture. Have you seen the IEA's net zero by 2050 roadmap in the news recently? People were talking a lot about how it assumes no new fossil fuel power stations should be built if we're going to hit that target. But it was a different part of it that caught my attention, its assumption of what is going to happen with carbon capture and storage over the next 30 years. So if you plot historical carbon capture and the IEA's roadmap projections, it shows us basically sitting at like zero for the last 30 or 40 years. Here's today, and then it basically just shoots up practically vertically. So this is one projection, but there are plenty of other net zero roadmaps that include even steeper projections for carbon capture in the future. And I mean, technology doesn't normally develop like that. I mean, I really wish that carbon capture was going to work. The more technologies that we can use to decarbonize, the better. But I am skeptical because we've been trying so hard for several decades now, and it's just not working so far. Or at least it's not preventing any significant amount of CO2 from entering our atmosphere yet. So I thought these projections were a bit weird, and I was wondering whether it's remotely plausible. And at that point, I realized that I don't actually know how carbon capture works. So I have no possibility to form an opinion on the technology and about its future development. I tried to research it, and I found lots of infographics and cute videos from oil companies that show basically all the CO2 is magically removed and then it goes underground and stays there happily ever after, the end. And if it's that easy, then why, after 30 years of talking about it, why aren't we doing it? So I found a carbon capture expert who would answer all my questions about the technology. Mark Allen is a chemical engineer who's been working for over 20 years in the industrial gases industry and has spent most of his career concentrating on sustainability. I spoke with Mark about how the most common kinds of carbon capture work. And in this video, I just wanted to limit it to carbon capture from fossil fuel power generation. That includes carbon dioxide that's mixed in with natural gas reserves that often just gets vented or flared. Then from gas or coal power plants, you can either burn the fuel normally and capture the CO2 from the flue gases, which is a relatively low concentration of CO2 mixed in with a lot of nitrogen. That's called post-combustion. Or you can burn the fuel in oxygen instead of air, so you don't have all that nitrogen taking up space in the flue gas, and that's called oxyfuel. And finally, we're also going to consider blue hydrogen, where natural gas or coal is converted into hydrogen via a steam reformer or gasification plant. In that case, the CO2 comes out the exhaust at around 5 to 15% concentration, similar to flue gases. So I've been looking into carbon capture methods, and there are a lot out there. And I found it really confusing to understand for people who aren't chemical engineers. So let's hear from Mark now about what kinds of carbon capture you'd use for which situation and how they work.
There's a few broad types of CO2 capture technology, but there's really only one that's used extensively through industry, and that's amine absorption.
All right, so can you explain how that works then?
Yeah, sure. But basically what happens is, in this case, with flue gas that has some CO2 and has nitrogen in it, right? When we pass that gas over or through the amine solution, right, the amines themselves, which are particular chemicals, basically reacts with the CO2 and grabs onto the CO2 and holds onto it pretty tightly, right? So everything else, all the other gas passes through, and you end up with a basically mostly nitrogen stream coming out, and then coming out the bottom of this vessel, you have this solution that is amine with some CO2 attached to it. Right? So then what we do is we apply heat, and that regenerates the amine, right, and drives off the CO2, so the CO2 comes off as a gas.
So that sounds pretty simple, and I can understand that. But then to actually make that work, then you need this, right?
Yep.
So
yep.
Everything
it's
like
the same,
a little
it's the same drawing.
the conical flask is this thing, right? The amine absorber.
Correct.
Is that right?
The amine absorber. Yep.
And what does everything else do?
Okay. So the two key things, right? You had two conical flasks on there.
Yeah.
One is the amine absorber. The other one is the amine regenerator. So basically everything else just moves the amine around, right? Or heats it or cools it. And it's all designed to be relatively efficient.
I've been looking at some of the operating CCS facilities, and some of them, I think maybe the one in Alberta, for example, only is capturing like 35%. Some newer ones, I saw there's a couple of retrofits in the US, Boundary Dam and Petronova one in, I think, Texas, that are getting 90%. And then all the reports, like serious reports, say that we can get 99%, but I'm just like, why can't you get it all?
Yeah, you're normally limited by economics in this case. A good case is actually LNG processing. So the CO2 can't be allowed to get into the cold part of the plant because it freezes before you get to LNG temperature. So you pretty much separate all of it out in that case. So you're running at about 50 parts per million in the treated gas. So that's a pretty good capture rate if you're going from, say, 12%, 15%, 30% down to 50 parts per million. The thing that stops you capturing it all in a power station, for example, ends up being economics, right? Because the amine absorbers are quite large pieces of equipment. They're to get the contact time you need, and particularly if you're trying to capture more and more CO2 out of it, you need bigger and bigger vessels, which then cost more and more money.
Is that the process that the longer you leave the CO2 in the amine, the more of it has this reaction, the more it's taken out?
Okay. So you get a higher residence time, but then of course, the CO2 becomes slightly harder to find, if you like, because you need bigger and bigger vessels to do this. And the economics of CCS are the thing that really holds it back.
Okay, molecular sieve. So that one I like because I found that that animation that can illustrate it.
And it's actually quite a good illustration of how it works, because it is just like a normal sieve. Basically, you pass this material through almost a grate, right? And some of it goes through and the rest of it gets caught. So molecular sieve works exactly the same way. And basically the CO2 gets attached to it or becomes part of that structure. Basically, one material is passing through the ceramic because it's a big bed of solid stuff and it's full, and there's a little bit of pore space in between, right?
It's like it's basically bowl of marbles or something.
Yeah.
And if you want to capture more, you just need like a longer tube full of balls. Is that it? Yep, that's right. Okay. So and basically you operate these in a two-bed system. So you have one that's doing the absorbing. When that's full, you can switch over to the other one, and then you regenerate that first one. And how do you regenerate?
So that depends whether it's pressure swing or temperature swing absorption. So with temperature swing, you apply a high temperature, it releases the thing that you captured. With pressure swing, you reduce the pressure and it releases the thing that you captured. And
is anybody using this, or where would you use it?
The air separation industry uses molecular sieves a lot, right?
Okay.
But they're capturing much lower concentrations of CO2. They're capturing CO2 out of the air, for example.
Okay.
Yeah, just because it's a cold process and you don't want CO2 freezing out in your plant.
You could use this for direct air capture then, or something.
Yeah. So the next one you're about to show, the membranes, I think.
Yeah.
So these are kind of similar, right, to molecular sieve. So it's basically a thin film, and you get some gases can pass through and other gases cannot, right? And these are becoming more popular, particularly in the gas industry, for places where you don't have a large footprint available to you. So if you were doing CO2 separation offshore, for example, and now you're limited here with space and weight, you'd tend to go for membrane technology because it's smaller than amines. In a normal natural gas plant, the amine scrubbing tower is the biggest thing on the plant by quite a way.
What about energy usage? Like, what I would really like to know is like how much does it reduce the efficiency, or what percentage of the power plant's output would be used to power the CCS? Do you have any sort of ballpark?
The answer is it depends. But yeah, I've seen a lot of material that suggests somewhere between 20 and 30% energy penalty is the sort of penalty you'd be paying to run a CCS project. It depends, obviously, on all of the things we're looking at. How much CO2 are we capturing? What is the size of the power plant, for example? But it's a significant percentage.
So, I mean, clearly, it's not going to be our only solution. We're not just going to carry on as we were, but with CCS on all of our coal and gas power plants, there needs to be some prioritization of the easy things that can be done with renewables need to be done.
Exactly. So, for me, and this is clearly my personal opinion, CCS is great for some of these really hard to abate sectors. So steel manufacture, hydrogen, but CCS on power starts to make sort of less sense when you start to compare it against the alternatives.
Okay, so I just want to sum up. So, I mean, you've got me convinced that this is all very normal. Engineering people in industry have been doing it. It does work, but we've got to reconcile that with the fact that we've been trying really hard for like 30 years and a lot of people really want this to happen and it hasn't yet. So what is your explanation for why we have these two things that really seem to be contradicting each other?
It's cost and business case. So in a world where carbon prices are low, let's be honest, they are certainly lower than what one would need to achieve the high rates of decarbonisation we require. CCS just doesn't stack up. For me, I think the economics have been one of the biggest barriers because it's all relatively mature technologies. So you don't see the same sort of like learning rate you get with solar PV or with batteries or stuff like that, because it's big process kit, right? And the cost of building a vessel won't change too much in the coming years. All of the pieces are there, and I don't think anyone's denying that CCS is an important part of the future, but like I said, it's about some of these hard to decarbonise sectors where I think it's going to get the most traction. It's going to be something like, how are you pricing carbon? That becomes the thing that really tips CCS, because I think it's absolutely a requirement, and we'll find it difficult to achieve decarbonisation goals without CCS ultimately. But, we just need that economic case to be there.
Thanks so much for that, Mark. I mean, you would not believe how much trouble I had as a non-chemist, non-process engineer trying to figure out how carbon capture actually works and whether it has the potential to mature into a cost-effective solution for emissions from fossil fuel power generation and blue hydrogen. So I guess the answer is that these types of processes that Mark explained today are already mature technologies. There are plenty of established industries where they have strong financial incentives to get rid of practically all of the CO2 from their product, either to ensure the quality of their product or to stop it from liquefying in their equipment and causing damage. So my takeaway from this conversation is that it's not the technology that needs to mature, it's the economics. The natural gas industry has a strong financial incentive to effectively remove carbon dioxide from their product, and so they have. but we haven't got that value yet associated with preventing CO2 from entering the atmosphere. And so we haven't. So in this video, we talked about carbon capture, which is obviously only one part of CCS or CCUS. And it's probably also the easiest, most mature part, because that's the part that's already mainstream in other industries. I'm going to find another expert to interview about the transport, utilization and storage parts of CCUS. So let me know in the comments if you have any particular questions that you'd like answered on that topic. This video also only really talked about the most mature, most mainstream carbon capture processes. But there are currently a bunch of emerging technologies that could present new opportunities in this space. So I'm planning a video on some of those techs as well. Again, please comment if there is a specific carbon capture technology that you'd like me to cover in that video. I want to thank my Patreon community for their input on this video. They suggested questions and concerns that they have on the topic. So if you want to help with suggestions for future videos and join in the chat group, then we would love to welcome you to the Engineering with Rosie Patreon community. Thanks for watching, and I'll see you in the next video.